Setting up the dependencies here, and then Chris just showed you how to register the parquet data with Athena. So what we're going to do next is if you open the third notebook, and I'm zooming in here a little bit as well so you can read it better. Hope this is okay. All right, so if you open 03, and what I'm going to do here, I'm going to do a quick run all cells. It's a longer notebook here, so I want to get the cells going. So feel free to do the same. And what we're going to do here now is to use Athena in our parquet data to run a couple of SQL queries and visualize the data set to see if there are some interesting facts. All right, here's a quick recap of the columns of the data set. So what we have at hand. And what we're doing in here is doing our couple of imports. So the Boto3 library, the SDK for AWS, the SageMaker SDK, setting the environment variables. And in this notebook here, we're going to use NumPy, Pandas, Seaborn, Matplotlib. So probably pretty popular libraries, Seaborn, Matplotlib, especially if you want to visualize results in the notebooks. All right, also a nice trick here, if you're working with Matplotlib, there's actually a setting to optimize the visualizations for retina displays, so the visuals come up a little bit more crisp and sharper here in the notebook. We're checking briefly here in that code, just make sure that you've run the previous notebooks, because this one requires that we do have the parquet data at hand. So this is really just some sanity checks here, and hopefully everyone at this stage has a true and an okay. Otherwise, you would need to rerun the previous notebooks. All right, and we're connecting to our Athena database, so the default one and the parquet table name. And we're using Athena here to run queries. And I'm also setting a couple of parameters here for Seaborn. So this is really just, you can see it here, axis, colors and sizes. And also a little bit of helper code for bar plots that I'm using here. And then we can get started. So we want to ask a couple of questions here and see what the data reveals. So the way we're doing this is we're starting to ask a question like which product categories are highest rated by average rating. And we're building up a SQL query here. And you can see here's the printed SQL query that answers the question, right? So this is a pretty simple one. Select product category, do the average of the star rating, and then from this parquet table in Athena, and then where the product category is, let's just limit it to 3. Otherwise, it's going to be larger queries here. Digital software, gift card, and video games. Group them by product category and order them by the average descending. And here's the result for those 3 categories. So you can see here that gift cards are the highest rated category by average with 4.73. Maybe I zoom in a little bit more.
Yeah, zoom in quite a bit. Yep, yeah, zoom in.
Yep, quite a bit. Yeah, I just got a big screen here today, so let me know when it's too small. All right. So gift card 4.73, and then digital video games and digital software is notably worse, so 3.8, 3.5 average star ratings. And what we can do now is we want to plot this, right? Visualize. So here's the code. I'm not going to go in details how to build those plots. Here you can see I'm doing a bar plot using Seaborn library, which has support for that. And then you just specify here the axis, product category, average star rating. You're passing in the data. And you can also add the title for the visualization, on the x-axis, which units the x takes here to use, labels for that. So pretty straightforward. Feel free to have a look at all of those code samples if you're interested. Let's just see the result here. Is a nice horizontal bar plot here, which shows us the results. And it's even more fun if you run this across the whole data set. And we've done this here in advance to the workshop and just give you the screenshot so we don't have to run all of the queries against the 150 million reviews here 10 times. So here's the results if you run it across the whole data. And you can see that gift card is really the top rated category. So I guess everyone is happy to receive a gift card. Nothing bad about it. And then you can see the average star rating going down And digital software is indeed the lowest rated, so 3.5. All right, and we're asking a couple of more questions. Which product categories have the most reviews? And again, here's the SQL query. So we're doing a count on the star rating and then grouping by product category and ordering by the rating. And you can see gift cards roughly have 149,000 reviews, digital video games, 145,000, and software, 102,000. And this really helps you if you're looking at your data and you're building up your training data set for the model to decide, depending on how large the training data should be, which categories to pick, right? Definitely, if you want to have more samples in your data set, you can check for the other categories. And basically, you can visualize, and this helps it even more. So here's the code to visualize. We're doing another bar plot here. And especially interesting here, not for the 3 ones, but if you look for the overall numbers. So again, depending on how much training data you want to get, if you want to get more in the millions, you could choose the books category. And if I scroll down here to the legend, you can see we have more than 20 million reviews in the books category in this data set here. And for our example here for this workshop, we want to keep the model training times in check. And also we're doing a fine tuning of a BERT model. Hence, we can go a little bit less here in the training samples. And we're picking categories that are here in the 100,000s of reviews rather than the 20 million. So here you can see the gift card, the software, and videos up here. All right. We're doing another fun query here. So the data set has as input the review dates. And we did some queries here trying to figure out when did the product categories become available on the marketplace. And it's not the exact science, but you could assume having in each category the first review. That should be around about the date when the product category got introduced, right? Maybe a few weeks later when the first reviews come in. So we just did that out of fun here. So here's the query. And basically checking for the minimum of the year, which is part of the data set. And if you visualize this, and here's to show how you can do like a time visualization. It's not too interesting for the 3 again. It's just one review. Basically in 2004, one category added, one in 6 and one in 8. But if you run this again against the whole data set, you can see that in 1999, there were 13 categories that had first review in that year. So this could mean that 13 categories got added roundabout in that year, or really just, a symptom of how the data set got constructed. But it's fun to see how you can visualize the different queries here. All right, and then we do a bunch of more queries. Feel free to check them out. We do a breakdown of ratings. So I'll just go quickly through the visualization. Basically, we're doing the count here per star rating, per category. And with that, we can build a stacked percentage horizontal bar plot. So the name is as difficult as the code to actually plot it. And then if I scroll down here, feel free to have a look later. You're getting this nice chart, right? So now we're stacking basically the percentages of the 5-star, 4-star, 3-star, 2 stars. And this also helps you to just, quickly get an understanding of how the data set is built and how many samples and which ones you might want to choose for model training. And also shows what we're going to talk about next is the imbalance of the data, right? So we can see that most of the review categories have a majority of 5-star ratings. And especially the 2-star ratings, nobody is really interested in writing. So if we want to build the training data set later, that's a good indicator that we should have a look to balance the data. All right, how many reviews per star rating? This is exactly across all of the categories, giving us this imbalance pretty nicely here in this visual. So we can see with the 3 categories we picked, it's, how much is it? 250,000 reviews for 5 stars. And only here, probably like a 10,000 for the 2 stars. And it's pretty much similar if you run this across the whole data set. People tend to really provide more positive ratings, 5-star ratings, and then less people provide a 1-star rating or a 2-star rating. You can also plot, go a bit a little faster here, the average star rating over time. So here is an example that shows how the average star rating developed over the years. And we can see in 2008, there has been, pretty low here, under 3 on average. So this is really coming more from the business perspective. So you probably want to analyze if it's a global trend across more categories, or if maybe one product category was the culprit. And then you definitely also want to see, if you're the product owner, for example, what's behind that, right? All right, and then if you do this across all categories, again, the 150 million reviews, it's a similar trend, not too extreme like with the one category above, but definitely with more and more categories, the average star rating has taken here a drop. It's rising again. And if you wonder that it stops here at 2015, this is when the data set samples stop. So the data set has data from 1995 to 2015. All right, going scrolling a little bit faster here. So here's an example if you do it per category, and you can see that indeed this 2008 drop was basically one category. If you look up the green, it's digital video games. So something happened to the video games in 2008. Not sure about it. But again, if you were to be the business owner, category owner, you would definitely want to know what's going on. All right, you can go crazy and plot this for, like, how many do we have? I think 52 categories. And then you're getting kind of a wild visualization like this. All right, another question, which star ratings are most helpful? And if you plot this, you will see that the 1-star ratings are actually marked as more helpful than the 5-star ratings. And I guess this also makes sense, right? We want to make sure we're buying good products. So we're specifically interested, at least when I'm searching, to look for any negative feedback and try to understand if this applies to me as well. So helpfulness definitely more on the critical reviews. All right. And you can go on here, more queries. You can do a ratio of positive to negative reviews, calculate that. And we also did a query here to analyze if you can see any weird behavior in the data. And for example, we're looking for a single customer ID and checking how often they're reviewing the same product ID. So normally, if you buy a product, you give it a review and you move on to the next, right? But here you can check, for example, if there have been a unique customer that reviewed the same product over and over, and what was the rating. And you can see, if you run this for the 3 categories, that there's a video game, Call of Duty, Black Ops 2, that got reviewed by the same customer ID. And again, this is random numbers with an average star rating of 5 for 10 times. And again, this could be a data set where, it just was copy pasted. Maybe the custom ID was, more often generated and just happens to coincidentally match to the same product title here as well, product ID. But it's kind of a fun thing to see off your data. All right, and it's also funny, if you look across all product categories, there's actually a video DVD, Pearl Harbor, from a unique customer ID, a random ID here, reviewed 130 times and has an average star rating of 4.2. So definitely a big Pearl Harbor fan in here. And also the second next here is a Shania Twain concert. Yeah. So I got rated. Yeah, Chris. Yeah. Aren't you a Shania Twain fan? Do you have anything to tell us?
I'm from Chicago. I might have been at that concert. What was the date on it?
Oh no, I don't know.
Yeah.
Yeah, when was the live in Chicago? I think it's.
I might
10
be
years. Is it older?
Yeah, that's DVD. So maybe I was in it and I was showing all my friends, maybe 110 times, or I just bought 110 copies.
You had a good time there at the concert, I can see. Yeah. All right. And then let's come back to our NLP use case, and I'm going to show you how relevant those queries are. So some of you might be asking, why are we asking all of those random SQL queries? And what has it to do with my job of building the NLP model? Well, if you think about the distributions, right, of the 5-star, 4-star ratings, you could use that as a distribution of the labels, right? Like how many in general, how many 5 stars are coming in for a specific product maybe, or product category. And if you analyze that and you have this baseline, you can compare this later when you have deployed the model and the live data comes in, and detect any, any drifts in the data. Are there more 1-star ratings coming in for a certain product that is against the baseline that you saw from the previous training data, etc. So it's giving you really good indications of label distributions, of review distributions, etc. Or like how many reviews are coming in for books versus other categories. All right, and the last query I want to show here before we move on to bias detection is really a very concrete example of the NLP use case. So some of you also asked, what is the BERT vectors and BERT embeddings? And we're getting there in the feature preparation step. Basically, you need to transform the raw text that is coming in into word vectors for NLP models to work with. And specifically for the BERT model, there's a parameter that's called the maximum sequence length. And that is a parameter you need to set, which defines how many of those input tokens to pass in one sequence. So in simple terms, if you pass in a review text, how many words, and words are not always a one-to-one relationship to the tokens that got produced, but just for simplification, how many of those words or tokens are you passing to the BERT model in one sample? And you can get a good indication, for example, if you're looking at the distribution of the review length here, the number of words. So this is the sample query here. So we're splitting the review body, which has the review text, by space. And this is giving us, if you do the cardinality, the number of words in each review. And we can calculate the percentiles. This is what we are doing here. So the shortest review, you can see here the minimum, the shortest review had 1 word. So this might just be a great, an okay or something, right? And then the longest review, the max, had 5,347 words. And if you do the percentile here, and even better, if you visualize it here as a plot, as a histogram, you can see the distribution has a very long tail. And you want to grab most of the reviews with that sequence length, but also you do not cater, you do not need to cater like for the maximum one, right? So looking here and checking with the percentiles, if you want to grab 80% of the reviews, they have 63 words or less, right? This is this first block here. So I think 80% of the data is a good catch here, right? Cut off this long tail. And we always choose and to optimize values and parameters. We always opt for a number powers of 2. So the closest one would be here, the 64 as a parameter value. And this is what we will be using as the maximum sequence length for our BERT model. And this is really just one of the parameters to tune the BERT model. And I'll show you here how you can actually get a good grasp of what value to pick based on the training data. All right, and this was the visualization notebook here. So hopefully that was interesting to you and get some insights of what we're working with here in the data. All right, and then quick check with you, Chris. Any questions before I move forward?
A couple people asking about the Kubeflow stuff, so I keep sending links to the Kubeflow. We're not doing Kubeflow today; it just takes too long, and we've done it in the past. So if you check out the YouTube, and also we do have code in here. We ask that you not run the code right now until we get through the workshop. You can run it in that last hour that we keep it up. We're going to keep the instances up for 1 hour afterward. And you could try the Kubeflow stuff, but please don't run it now because we won't be able to support you. Yeah, so let's see. I think that's it. Yep.
Perfect. All right, so let's move forward. And if you open 04, we are working now with bias detection. So probably most of you heard about biases in data, in model predictions, etc. So it's an important step in building a machine learning model to make sure that you're eliminating as much bias as possible. So there's various places where bias can get introduced. So the first step you want to make sure is what we're doing here to detect bias in the actual data set. And I'm going to explain here what I mean with bias, because there's different ways to interpret this. It's not always, the most prominent one is definitely if you're favoring specific groups, if you're favoring, let's say, if you're writing a loan approval algorithm and maybe the algorithm favors specific age groups, right? Maybe age 30, 40 is preferred and the loan is approved. Maybe it disfavors younger generations, maybe older age groups. So this is a very obvious bias where one specific group is favored over the other. But bias also includes, for example, a class imbalance, right? And I'll show you this here when we run this notebook. So let me actually do this. I do a run all cells because we're running some jobs in here. So if you want to do this as well, just make sure this notebook is running. And here's a great article published by the Amazon Science team, which does a lot of research and publications. And they're describing here in this post, if you follow that link, how Amazon SageMaker Clarify, that's the functionality within SageMaker to help you detect and mitigate bias, how that works and how you can use this. So it's a really good read if you want to follow up on that after the workshop. All right, then to understand bias a little bit better, it's important to understand the terminology. So what we're using here is a few new expressions, a few new terms I want to quickly introduce. So in general, when we talk about the bias, it's really coming down to an imbalance in the training data, right? You might have more examples of the groups that are ending up being favored, right? Because you just have more of those samples in the data. If you're thinking of our use case here with the product categories, we definitely have in the gift cards category, we're favoring the 5-star ratings, right? Because we have almost 90% 5-star ratings in there. So we definitely have an imbalance of data already, which we've seen through those visualizations. So in general, the bias is an imbalance, which might lead to a behavior where the model, favors specific groups. And in general, obviously, this is like the very sensitive ones like age and gender and such things. But it can also be really kind of data points like in our data set, right? More 5-star ratings compared to the 1-star ratings. All right, so to calculate this, we need bias metrics. And bias metrics are the mathematical metrics to detect in the data or in model predictions if you have like more positive labels compared to the negative ones, etc. And I've shared a link here, if you click on that, that shows you how to define the metrics, but also has an overview of all of the available bias metrics and how they're calculated, right? So the most obvious one, as I said, is the class imbalance, which is the imbalance in the number of members between the different facet values. And I'm explaining facet value here in a second. So here are all of the descriptions and also more information if you click on there. What's the mathematical formula to calculate that? So again, there's specific metrics that we're going to calculate, which give us an indication of potential bias, and then it summarizes in a report. For the data that we're passing in, we do need to specify the label. So the label is basically in supervised learning, the target column, the value we're predicting, and here we're providing the label in the supervised training data set. The positive label value, so in our case, the label is the star rating, right? And the positive label value is, in our case, we're going to say the 5-star rating, maybe also the 4-star rating. So 4 and 5 are the positive ones, right? And we're comparing that against the negative ones. In our case, that would be unfavored. Nobody wants to get a 1-star rating, a 2-star rating. And this is how we're checking if the data is favoring, for some reasons, the positive in categories, right? Then the other two important terms we need to understand is facet and facet value. And the facet is the column or the feature. Think of it as the column that contains the attribute we want to check for bias. So again, in our data set, we're going to use the product category as the facet. So to see if we're favoring, for example, in the gift cards, more the 5-star, ratings, if gift cards is favored over digital software. And the value is then the individual category, right? So facet is product category, and the value would be gift card, would be digital software, etc. And we will see this in action here in just a second. All right, and then those are the metrics that are available as part of SageMaker Clarify. That's the tool that calculates the bias. And those are the metrics that are getting calculated for the data. And the data bias, we're also calling the pre-training bias. You can also check bias after the model has been trained, because also the algorithm and the model itself can ingest new bias, right? Coming from the algorithm you're using, etc. So there's a step of checking the bias in the data, pre-training, and then there's also the step of checking any biases after the model has been trained. And you can even check this, as I said, when you deploy the model in production to monitor and calculate the metrics and compare them to the metrics you calculated after the training to see if there's a drift. And maybe you define a range of values that are acceptable, right? And once you detect that those metrics are outside of the thresholds, you can raise an alarm and say, okay, this model is showing, is drifting off the metrics that it's supposed to. So depending on the data that is coming in. All right, so enough for the introduction here. Let's get started. So again, this is just the boilerplate code. We're pulling in here the SDKs, setting the environment. And what we're doing now, so let's build 2 data sets, and we've prepared this. So let's pull in here the reviews from the gift card. So in this case, we're pulling in here the TSV, tab separated data. Let's pull in the software. Let's pull in the video games. So let's use those 3 categories. That's the raw data. I'll concatenate those here in the data frame and the pandas. And we have the raw data. And if we visualize this, as you can see here, we can see very strong that the data is imbalanced, right? So as we already knew, a lot of more 5-star ratings across all of the categories. So blue is the gift card, orange is the software, and green is the video games. And yeah, highly imbalanced across everything, across categories and even across the star ratings. All right, so let's upload this CSV file to S3. So everything SageMaker works with, we have to have the data in S3. So we're just uploading this here with a session upload. And then what we can do is we can run the bias analytics. And we're doing this by importing Clarify, the library here from SageMaker. And we're specifying here an output path where to store the results. And then we're starting configuring Clarify. So the first step we're doing here is the data configuration, where we're pointing to where is the data to analyze and where to write the report to. And then we're providing here the label. In our case, that's the star rating, and the headers of this input data set. And we're also specifying this is text data, CSV data. All right, so Clarify knows where to find the data and which one is the one to predict the star rating. Then we're specifying the actual bias configuration. And you need to specify here now this sensitive column. So in general, you could, for example, pick the gender, right? If you want to check if there's a specific bias towards a specific gender in your data. In our case, as we're working with text data, our facet is the product category. And then you're also specifying the label values. And these are the favorite ones, right? The positive outcome. So if you're working with gender and you want to check if the data is favoring the women, you would use that as the value. In our case, the favorite label is the 5 and the 4. All right. So with that, we can specify the actual job. And SageMaker gives us processing jobs. And processing jobs is a construct that takes code and then spins up instances in AWS to execute this code against your data. So a good example is to do feature engineering, data pre-processing. You can use them. And there's also a specific implementation of those processing jobs already built in for SageMaker Clarify. And this means that that image that gets deployed on the EC2 instance already has the Clarify libraries installed. So in here, we just need to pass our IAM role, which gives permissions. You can specify how many instances. So here we're just using one instance of type M5X_large, passing our SageMaker session. And this is basically the execution environment where to run this job. All right, and then we can start the bias. So we're calling on this processor object, we're calling the run pre-training bias, passing in the data config, the bias config, and you can specify which metrics to calculate. So methods is basically the bias metrics. You can just specify a few of them, or you can run all. And this kicks off the job. So we do have here quick the deep links. So if you click here, this takes you to the console. And here you can see the processing job that in the meantime has completed. I think this one just ran for 5 minutes roughly. And you can see here again the specific image. That's a Docker image that got used. And you can see the instance type that we specified, instance count, and a lot of the configuration values here. The input data set that we used, that is our CSV file. And also the outputs here ending up in an S3 bucket. All right, so this is this. You can also check the CloudWatch logs for the job if you want to see what's happening inside. And then here's a link to the S3 output folder that we specified. And here you find the reports that got generated, the bias reports. And I think we're also pulling it down here. So we're waiting for the job to finish. So this took 4.5 minutes here. And then we're pulling down this report that I just showed you in the S3 bucket. So here's the link. And this opens up a nice HTML report directly here. We downloaded it to our studio environment. And you can now see that the job calculated the metrics for the different categories. So here's, for example, category gift card. And you can see here that pretty much all of the metrics show specific bias. And you might ask, what does the number mean, right? What does it mean if I have a class imbalance of 0.24? What does it mean if I have this DPL value of minus 0.27? And you can find the explanations if you go back again to that link that I shared earlier in the notebook that describe those metrics. So for example, yeah.
Can you zoom in way far? Yeah, I
way
know.
More.
Monitor, and I didn't realize. It's huge on our monitors. Yeah, Ansha and I have the same exact monitor, and it seems big, but it's not big enough.
It's better? Yeah, just let me know. All right, so if you wonder what the values mean, right, have a look at how they're calculated, and then there's an explanation what it means. So for example, the class imbalance is basically here the formula. You're taking the number of samples for a facet A, which is, let's say, the gift cards, minus the number of samples for the other category, which might be, in our case, then the software and the digital video games, divided by the sample plus the other samples. And this will give you this metric, and it's normalized in the interval from -1 and 1. And if you're getting a positive value, that indicates that the facet A gift card has more training samples in the data set, and the value of 1 indicates the data only contains members of the facet A. So if this ends up being a 1, gift cards would be the only category facet with samples here. And if it's a negative value, that indicates that the other compared facets have more training samples. So this always gives you kind of an explanation. And similarly, if you go to the other formulas here, so the difference in proportions of labels, DPL, basically compares the proportion of observed outcomes with positive labels for a facet D with a proportion of observed outcomes with positive labels of facet A. So in this formula, if you see here, also ends up in the specific range of -1 and 1. And if you're getting a positive value, this indicates that the facet A has a higher proportion of the positive outcomes when compared with the facet D. And in contrast, the negative value indicate that the facet D has higher proportion of positive outcomes compared to A. So this is really always taking the stand of one category value and comparing it against the others with all of those metrics that are available. And if I look back here to our report, now you can see there's a higher imbalance from the view of the gift cards. Here is actually a -1 in comparison to the others, etc. So this gives you a good indication, and you can see it iterates here through the different facet values, right? So for each category here, it's calculating those. All right, so we know our data set is biased, right? So what can we do? So what we can do is to balance the data, right? Want to make sure that we're not feeding our model data with a data set that has definitely more 5-star ratings in one category than the other. So what we prepared is the same CSV data, but we basically balanced everything, as you can see here. So for each category, we have the same number of samples for each of the star ratings. So we're not favoring any gift card anymore over video games. And let's use this data now and recalculate the report. So we're doing the same thing. So we're just using this slightly changed CSV that is now balanced, uploading it to our F3 bucket. And then we're doing the same configuration here, the data config, star rating is label. The bias config remains. The favored positive label values are 5 and 4. So all the rest are the negative, unfavored ones. And we're using product category. And we're starting our processing job that calculates those metrics against the data. All right, so, and again, if you have, the nice thing here is if the data set is getting larger and larger, you just really have to store your data in F3, and then you can spin up here more instances, right? So if you're increasing this, not for today's workshop, but this only takes 5 minutes, but if you have more data, you can increase this to, let's say, 5 instances, 6 instances, whatever you need. And it's paralyzing the effort, so you can scale out and do this across also large data sets. All right, we're running the processing job here. And in the meantime, this job should have also completed. So here's the second processing job. And this is basically the F3 output data. And it's in the data balanced, and I zoom in again, in the data balanced folder here. And here's the results from the second job. So let's see, also taking 4.5 minutes. And I'm clicking here on the report, the balanced one. And here we can see that the values are now zeroed out, right? And you might wonder why class imbalance still shows a 0.33. This is because we have 3 values in here, 3 categories, right? Facet values: digital software, video games, and gift cards. So if we're combining all 3 of them, we're having 100%, which is complete balance. But from the view of one category only, there is 2 times the number of samples in the others, right? So as long as those add up to 100, we're actually in good balance here. And you can see that all of the other metrics went to 0 because we have now the super balanced data set. All right, so this is the quick introduction, how you can run bias analysis and how you can actually make sure to balance and make sure your data is not ingesting any bias into the model training. And as I said, you can also use Clarify in the same way to run post-training metrics once you've trained your model. So let me quickly check where we have the call. So here you can see when we started this processor job, we called run pre-training bias. So there's another call that you can do when you have a model that has been trained, and then you can run post-training bias, also providing model information, and then it's calculating specific bias metrics with your trained model. So definitely an important step to do in making sure when you prepare the data. All right, and this was the quick sample here of detecting bias. So how are we doing, Chris?
Yeah, good. Got a question about what is a facet exactly, and I'm just explaining it's the same as a column. And we're looking for a potential imbalance in a particular facet or column relative to the star rating of 4 and 5. So, you know, typical bias talks about sex and age and, you know, sex, gender, age, things like that. Here, it's not as sensitive of a facet that we're analyzing, but since we don't have age, since we don't have gender in this data set, we are using product category, and Ansha's highlighting where we are. Our data has much more data for, you know, books. That's one imbalance. That's just number of reviews, which when we go to do our feature engineering, we will balance that out. Now we've taken it one step further. Ansha has shown that relative to a 4 and a 5, which are positive sentiment, you know, positive reviews, there is clear imbalance, and that is relative to product category. So specific product categories, so yeah, here like gift card has a much higher ratio of 5s, you know, relative to 2s, for example. And so in the next, you know, couple notebooks, we'll be balancing this out and making sure that our model can produce fair and unbiased predictions. And yes, we can check combinations of facets as well. Yes, we're not doing that here. That actually came up yesterday as well too. Let me add a GitHub issue, Ansha, for us to address that because it's come up more than once, the facet list.
Yeah. All right, and then let me close this one. We're moving on, and we're almost at our first model pipeline. So what we want to do here in the notebooks 5 and 6 is to give you a bit of an understanding how BERT models work. I guess not everyone had the chance to familiarize themselves with it. And what we're going to build in the pipeline is basically we're training a BERT model. So we're using a pre-trained BERT model, as Chris has explained in the beginning, a Hugging Face library, the still BERT model. So this has been pre-trained, and we're fine-tuning it to our data set to predict and classify the star ratings. So to give us a better understanding how those steps work, we have two notebooks here prepared. So 05 gives us a little bit of introduction, and the question had come up a couple of times in the chat already. What are those BERT embeddings, right? I heard Chris talking about BERT vectors, BERT embeddings. So what are they really? And yeah, Chris, do you want to take over, or shall I do this one?
Sure, keep going.
All right, so I've put it here, first of all, a link to the paper. So if you want to read up on the BERT paper itself, here is the research paper back from October 2018. BERT has really kind of revolutionized the NLP space. It introduced a new architecture based on transformers. And if you wonder what the heck are transformers, that architecture got introduced actually, I think the year before in 2017. Yeah, in June 17, in the paper, Attention is All You Need. So they introduced, the authors here introduced this transformer, not the transformers, I think, but yeah, it's the transformer. But more specifically, the attention mechanism. So that's the important piece here, that is giving the model the ability to really look at the complete surrounding words, the complete sentence, if you will, to help NLP models become much more robust and improve them. So this has been really kind of a breakthrough in NLP research. And then BERT used that attention mechanism and did some slight modifications on the transformers to add this bidirectional encoder. Just for those of you who are interested in the details, definitely worth having a read. For all of us here, let me run this notebook. So it's getting executed. So I've started to kind of try to visualize this to help people understand. Oh, I'm getting the wrong direction here, huh? Here we go. How this works, right? So your input is raw text, right? So for example, I love this movie. And in the first step, this raw input gets tokenized. And there's various techniques and various algorithms how to tokenize. What BERT uses is called the word piece tokenization, which is really just one sample algorithm to tokenize. And there's many more. There's sentence piece, word piece, etc. And this is not representative. I just made a very simple example here. Tokens doesn't necessarily need to be the full word, right? It's applying stemming very often. So it could end up, especially if you're using longer words and plural, in just, stems of the words. For some simplicity, I just showed you here. So there are special tokens getting introduced, for example, CLS for a classifier. And then whatever this algorithm ends up in the tokens here, for example, here we would have 4 tokens. And then what happens in preparation here for BERT is that we're creating the input ID. And the input ID is basically a lookup of the vector representation for that token. So the pre-trained models here, they're coming with a vocabulary. And we're basically checking in this token and saying, okay, which vocabulary entry is it, right? And this might up here, the input ID 101 is actually the classifier token. So for love, this would be, for example, maybe input ID 392. This would be input ID 25, and movie would be 123. So this is really the index, let's say, of the vocabulary. And then BERT works with those 768 dimensional vector representations. So this would end up like one sample here with the 4 tokens, and each has a dimension of 768. Then there's an input mask. And the input mask is if you're passing in, let's say, very long sentences and therefore long sequences of tokens. At one point, you either truncate. This is when we use the 64, if you remember, the maximum sequence length. Or if our review has only one word, so with this classifier token, we would only have 2 we would pad up to that 64. And then the padding would end up in being zeros. So the 1 really just shows which tokens are like really to pay attention. And the 0 means we just padded. All right, and then segment ID is less relevant. This is really just if the use case is question answering, and you have 2 sentences which you're passing in for the question answer. The 0 would indicate sentence 1, the 1 would indicate sentence 2. In our case, we're doing classification. This doesn't even apply, so we don't have to think much about this. And then we do have a position embedding, and this is really the index in the input sequence, so 1, 2, 3, etc. And what BERT does is it's doing the element-wise sum of all of those embeddings. And this is basically then this final embedding that it's getting passed to the BERT model. All right, so this is really just a very rough overview of what those BERT embeddings are. And here's a quick screenshot. We will get to this at the end of the notebook. But here's a sample how those look like. And this is an example from the feature store we're creating. So here you can see those input IDs for 3 samples. Again, the 101 is this classifier token. And then you see here the IDs, which are the IDs in the vocabulary. Input mask here is 1. So those are real tokens. Segment IDs is always 0 because we only have 1 sentence. And then what we're also passing in here is a label ID. And if you see, this is really just mapping to the actual label, the star rating, but it's the 0 index. So the star rating of 1 is the 0 index. The star rating of 2 would be 1. The star rating of 5, etc., is the index 4. All right. So this is a rough overview of those embeddings. And what we're doing now in preparation for the training is to create those BERT embeddings from our review texts, right? So if you remember, those data sets do have the star ratings as the labels. And we're gonna use the review body, which is the review text. And in a first processing step, we're creating those BERT embeddings that I just showed you. So we're using, again, a SageMaker processing job. In this case, not to run Clarify, but to run our feature engineering code. So what you can do is to write a simple Python code that is processing the data, and then you're giving the processing job your code, and it will apply it on the input data. All right, so the goal is here, again, to create those listings out of our raw review text. So for every sample, we need to have the input ID, input mask, segment ID, label ID. And we're using TensorFlow here as the framework. So what we're also doing in the same step, we're splitting the data into training, validation, and test data sets. And then we're also writing that as a T of record file just to optimize for the training with TensorFlow. All right, so this is the job at hand. And here we're doing just a quick implementation in the notebook. We will show you how we run this as part of the pipeline in a second. All right, so we're setting up the SDKs here, and we're pulling in a couple of libraries, TensorFlow, what we need. And then the first step of tokenizing, we're using, if you remember, pre-trained BERT model from Hugging Face to still BERT. And the great thing about those libraries, Hugging Face also provides the tokenizers for each model. So what we can do is here, this call basically pulls down this tokenizer from the Hugging Face library. So we're saying we're using distill BERT, base uncased, this is the type of the model we're using, and pulling down this tokenizer for that model. And that basically implements all what's needed to create those right tokens. So we're specifying here review body is the text. We're also keeping track of a couple of other things, star rating, the label values. And label map is basically just doing the mapping, as you can see here from the label and here in the ID. All right, we're creating a class for the input features, and the features consist here of the input IDs, the input mask, segment IDs, label ID, review ID, date label. So this is really just what we want to slam in here as part of the feature that we're creating. And the actual input that is coming in, the raw input, is basically the text, the review body. We're passing in an ID, the date, and setting here the values. All right, and then we're doing a convert input function. So this is taking the input, and you can see here we're passing in this parameter. So the number of sequence, the maximum sequence length, the number of tokens in a single sequence. And if you remember, this is why we calculated the 64. So if our review text has 5,000 words, we tokenize it and we're truncating at 64. If the review comes in with just 4 tokens, we're going to pad it up to 64. So this is the magic parameter that we need to specify. All right, and then we're really just here calling this tokenizer and passing in the text from the input. And the input is basically this input class that we defined. All right, and then we run the tokenization and passing in here the input text and say we pad. So this means if the review again is too short. And here again, this parameter maximum sequence length. All right, and then we can grab here the input IDs, we can grab the attention mask. And then here we can just set the segment IDs, it's 0 in our case, get the label ID, and returning here the features as input features object. And we're printing it. And then we do have another function here which transforms the inputs to the TF record files. So this basically iterates here over the inputs and then adds the, takes the individual features here and then basically converts them into TensorFlow features and then writes out with a TF record writer a TF record file. And we're also returning the records as is. All right, so again, let's see how we can run this here. And here we're doing just, again, in the notebook a sample calculation. So again, we want to get input IDs, input mask, segment IDs, and the label ID. All right, and we're also gonna store this in a feature store. So the good thing is when we're preparing those features, many of your coworkers might need the same features, right? And we don't want to do this over and over again. So recently, the concept of this feature store has become very, very popular. So this is really kind of, think of it as a store, could be online or offline, depending on your needs. On offline store would be implemented here with F3, where you're storing those features so others can then query the feature store and also retrieve those BERT embeddings, for example, right? And so we definitely want to store those so not everyone in the team has to recreate those every time. So this is what we're going to do here. And we need to add an event time. That's just the format that the feature store requires. So we're doing here a timestamp calculation. And then we're creating here some dummy data, really just to keep it easy in the notebook. So let's say we do have the label 5, we have a review ID, and we have a review text. Let's do just one sample for 5, 3, and 1 star rating. And we put it in here in a simple pandas data frame, giving it the column name, star rating, review ID, review body. And then we're applying here on this data frame the input. So we're converting here the label column into the label, the review body column into the text, and the review ID into the review ID, and the timestamp to the date. All right, and we can double check. We can, for example, now pull out the date here. This looks good. Feature store actually requires a specific ISO format, so we're just making sure the date got converted correctly. And then we're also here specifying where to store the TF record file. And then let's create the feature group here. So first of all, here we're calling this feature store definition. So we need to specify how our features look like before we ingest them. So this is the feature definition. We're passing in here the input ID, input mask, segment ID, etc. Everything we have. And then we can create the feature group. So the feature group is basically logically grouping features of the same type. So we're giving it the feature group name that we specified above, pass in this definitions and the SageMaker session. And this gives the logical definition. And then we specify the record identifier, so how to query for the records, and this will be our review ID. And then, as I said, it requires an event time, and this will be the date. All right, so we give the feature store a name using the timestamp. And then we're creating this feature group here, passing in the S3 location. So this is for the offline store, passing in the definition for the identifier and the event time role. And you can also enable at the same time an online feature store. So every feature that is checked in will also be available in an online store. All right, we can describe the feature group. So you can see here all of the definition. And we wait for the feature group to become available. And then what we're doing is we're generating now the inputs. So here you can see that we're calling the transform inputs to TF records, which will also call the other function to generate all of the inputs. So we're passing in the inputs, we're specifying the output TF record file, we're passing in the maximum sequence length, and this will basically now run all the code that we showed above. And we just passed in the 3 samples, so you can see here, it's printing out the tokens, it's printing out the input IDs, the input mask, and the segment ID, label ID, review ID, date, and it's doing the same for the other 2 samples. All right, and with that, we can then ingest the records into the feature store. So again, here we have the records in the pandas data frame. What we're doing is we're adding here a column and saying for the different split types, especially we're doing this later at large scale, where we're going to split into train, validation, test. Here we're just adding that this is, for example, for train. So this makes it clear if you want to filter later and check out features for a training sample or for test samples, etc. All right, and with that, we're almost done. So we're just making sure that the objects are of the correct type. So when the pandas data frame comes back with an object, we're making sure that it's casted to a string. All right, and then we do the feature group ingest, passing in the data frame with the records. And we can also scale this if we need to, maximum workers. And after that, we can query. So let's say we want to get a record. So again, we do this by the record identifier. We specify the review ID, and here we go, just grabbing the sample one, and then you can do this feature store runtime client and get record, passing in the group name and the identifier. And this gives you, as you can see here, the record. All right, this was the background to the feature engineering for our BERT model. And I'll check in with Chris here for questions.
Yeah, a lot of questions. I realized too that maybe we didn't make it clear that previous sections were ingest and then analyze, and Ancha then jump, and then we were detecting bias, which is really part of the analyze. And then Ancha jumped into feature engineering. So this is all in the context of converting our raw text into numbers. Machine learning algorithms like numbers and vectors. They don't like raw text. It doesn't mean much in mathematics. So we have to convert it to something where we can use linear algebra. So yeah, so that's this step. And let's see. Asking about online versus offline. So I think somebody, Kalish, responded well here. Online feature store is more for inference. So the power of a feature store is you can make you can do these BERT transformations, for example, one time and store them to be used later. And now, so like the next time, let's say we want to either train a model with these same reviews, we could go straight to the already transformed features in the feature store and just use those. So that would be offline. Online is much faster access and meant for a different type of workload. So you have two different workloads in our world today. We have training the model, which is really batch and kind of row-based, and then there's more on like the inference side. Well, actually there's three. So there was analytics, which we used Parquet, which was a columnar format. Then we have training, which is really row-based, and batches, because we always want to train on batches. Gives us higher throughput, gives us a broader view of the data set. While we're training, we're shuffling in between. So every time we pass through the data, we see the data slightly differently, but still in batches. And then we have inference, which is actually making predictions. So for example, someone, a user of Netflix, like I'm going to do here in a couple hours, I'm going to finish up a show I'm watching. I'm going to log in, and Netflix's server, instead of, pulling in my account profile, which, might be mildly interesting, they're going to pull up a vector, a BERT vector version, for example, of me, and then use those in calculations to make recommendations. And instead of regenerating these embeddings, they're called, each time, we store them in this feature store. And therefore, when I log in, the Netflix server just pulls in quickly this vector that's already been pre-built, and now can start filtering and doing all kinds of fun stuff. So yeah, and roughly the offline feature store is backed by S3. And has lots of features on top of it for time travel. So the other benefit of a feature store is I could actually back up to what the data looked like, last year. So let's see, what was Chris's preferences last year? Let's train a model. Now let's fast forward and pretend and go to current day and train a new model. And maybe Netflix knew me better last year than they know me for whatever reason. Maybe my patterns, after life goes back to normal, maybe I won't be watching the same types of shows. And so they could actually time travel and possibly do an A/B test on two different models. Chris from 2000 or from 2019, and then Chris from current day, and start to do some very interesting tests. Yeah, and then the online feature store is backed by Dynamo. And in the past, people have built these things themselves. In fact, there's a lot of reference architectures on AWS that describe feature stores. Feature store was just launched at reInvent 2020, so just a couple months ago, which is why we want to show it. But people were building this themselves. And we saw that there was enough customers building this themselves that we decided to then build this and offer it as a service that has all the best practices that we see across all of our customers and see these usage patterns. So feature stores are still an emerging concept. And if you haven't done a whole lot of machine learning modeling, this probably doesn't make sense to you. And might not make sense until you do go work for one of these companies or start to really see the value. There's some startups here in the Bay Area. There's actually startups across the world that are working on feature store. I talk regularly with my friend here in town that has his startup for feature stores. And one of his challenges is to sort of educate people on why we use feature stores. And so yeah, we're showing you kind of how to use it, giving a quick sample use case. But yeah, and in fact, I think our previous webinar that we did on Monday, just a few days ago, which I posted to YouTube, has the whole, we have two talks. We have a full hour on feature store. So yeah, check that out. Okay, a couple other questions. Yeah, Ancha, how do you want to proceed here? Where are we at?
So do you want me to do the training and then you kick off the pipeline?
Yeah, and then before we take a break, we have to run 07. So
Yeah, let me give a good walkthrough here to understanding what the fine-tuning step does. Then we're kicking off the pipeline 7, and after we've done that, we take a break because the pipeline will run for a little bit.
yeah,
So I think that's good, and then you can walk through the pipeline after the break.
sure. And pipeline really is just going to be a summary of what we've been talking about here. So pipeline's going to be doing the feature engineering. It's going to be training the model. It's going to take a look at the model, see how the accuracy is, and then finally deploy the model. So yeah, let's try to take a break at the top of the hour. So yeah, let's get cool.
Yeah, all right. All right, so we've talked through the feature engineering, right? How to process the raw text into those input IDs, segment IDs, etc. What the BERT model expects as inputs. All right, let's move on now. We've prepared the features. We stored them in the feature store. Next is we want to train our model. And I want to quickly show you and introduce to you the concept, if you're not familiar, of pre-training versus the fine-tuning of a model. So especially in the NLP space, training an NLP model from scratch can take very long, right? You want to train the model on large text corpuses. Imagine you're training it on the whole of the Wikipedia, right? If you're training the model for English language, you're training on the whole of the English Wikipedia. If you're training maybe for French language, you're training on the French Wikipedia, or large collections of book corpuses, really, right? So this generic pre-training takes the biggest raw text that you can find, basically, and this can run for days, right? And depending on the model, there's a specific implementation. So BERT, for example, has 2 steps. So it runs in parallel the masked language model, where it basically randomly masks a certain percentage of tokens and forces the model to predict the masked one, just to get more robust in predicting the word. And also it joins 2 sentences to random sentences sometimes and lets the model predict whether this is the next sentence. So whether, they follow each other, and the model has to predict, yes, that's actually a following sentence, the first one, or no, that's just a random combination. And this is running as part of the pre-training, and pre-training is an unsupervised step, right? You're just providing a text corpus and let the model learn. And once you have those pre-trained models, you don't have to do that for everything you do, right? This would be insane. This is why it comes in handy in using those pre-trained models that already have all of this step done for you. And this is what we've been doing. So we've been checking out a distilled BERT model that already has been trained. So what we're doing here in our training is actually a fine-tuning, and this is the supervised step, because here we're providing our data, so our domain-specific data, which means your company data, your specific use case data, right? If you want to train the model in maybe classifying research papers, you have to train it on research paper data, right? So this can be a smaller subset. It doesn't have to be the large extent as the Wikipedia, but it's introducing your specific terms that you need the model to recognize. So in our case, this is the customer reviews data. And then you're also adding and specifying a layer, whether you want to do a classification, which we're going to do, whether you have a question answering problem to solve, or whether you want to do a named entity recognition. So depending on the NLP use case, you're adding the additional layer on top. So what we will do, we add a text classifier layer on top of the model and teaching it to classify the star ratings. All right. So this is basically the steps. You can, of course, pre-train your model from scratch if you find that you have enough data and it's very specific. For our use case, customer reviews, we assume that language is pretty much used probably in Wikipedias already. So many of the tokens should be recognized and available in the vocabulary that got built in this pre-training phase. All right. So coming to our use case here. So we're using a pre-trained model. We already created the BERT embeddings. And now we're in this fine-tuning step. And also, if you've been working in computer vision, maybe you've heard of transfer learning. So think of fine-tuning as the transfer learning for NLP. So it's a similar idea of applying the knowledge that the model already acquired to a slightly different problem. All right, so we're fine-tuning with our data, and we're adding this classifier to predict the star label. All right, and let's actually run the notebook so we see how it's been done. All right, pulling in here a couple of libraries, and note here that we're pulling also from the transformers. That's the Hugging Face library. Again, the tokenizer for DistillBERT. And we're using this specific model. So we're using a TensorFlow model of DistillBERT for sequence classification. This is what we're doing. And there's a couple of more libraries we're pulling in, the config, and the pipeline actually helps you if you want to run predictions in the notebook here with a model. All right, we're specifying some helper code here to select the data and the label from the TF record, as we're reading now TF record files. And then here is basically the code that creates the data set from the TF record files. So we're passing in here our TF record file names. Again, the maximum sequence length that has to be carried through each step. So also if you're training, you have to pass this in so the model knows what is the sequence length here that the data got prepared for. All right, and then we're basically here reading the input files as TF records, creating the TF record data set. And we're creating here, we're passing in the features. So the input IDs is a TF-IO feature of this type. So we're specifying the types here, similar to the input mask and the label IDs. And here's the helper code to also decode a record that is used inside. So this one takes a record and then returns a single example. So this is really just the TensorFlow object type that it's needed. All right, and we're applying this to the whole data set. Okay, so with that, we can specify the path where we have the TF record. So here is, for example, the BERT train. This is the split for the training sample. So we have split the data into train, test, and validation later. And here we're just pulling in a sample from the training split. And we're looking for all TF record files in that folder. And here you can see we're printing. So here are the 3 TF record files. All right. And with that, we do have also the folder for the validation data and for the test data split. I think in here, it's just really, we're using 2 categories actually to make it simpler. All right, and then we're specifying the hyperparameters. So let's just we're running this inside of the notebooks. Let's just do one epic, very, very simple, 10 steps per epic, 10 validation steps. Setting a learning rate, setting the epsilon value. So this is really just the hyperparameters, the maximum sequence length. And then we load our pre-trained model. So here you can see this call again. So DistillBERT config from pre-trained. This is calling the Hugging Face configuration for those models. And we're setting here parameters that are needed. So the number of labels is basically the length of this classes here, which has our star ratings. And then here we're doing this 0 ID mapping. So the 1-star rating is ID 0. The 2-star rating is ID 1 and back and forth here. All right, we can print the config and then we can start building our model. So here we're loading the pre-trained model, TF DistillBERT. So TF means it's the TensorFlow version. And this is the type, and we're passing the config. And then we have here our pre-trained model available. We're setting here the input IDs. So as a TF Keras layer input of the shape max sequence length. And also the input mask here is a Keras input, also shape, hex sequence length. This is why it's important to use the same parameter. And then we're creating here an embedding layer. So we take the model, the BERT, and set those parameters with the input IDs, and attention mask is the input mask that we generated. And then we're adding here another layer on top. So we do a TensorFlow Keras bidirectional layer here on an LSTM, setting dropout values, etc. And adding a couple of more, a global pooling layer, a dense layer, a dropout layer, another dense. And this is basically then our resulting model. And here you can see the activation sigmoid as the last layer, as we want to predict and classify for a single class here from 1 to 5. All right, so we've built our model, and we're specifying the loss function. So we're doing here a sparse categorical cross entropy. We're specifying the metric, and we check here for the categorical accuracy, using Atom as our optimizer with the specified learning rate and the epsilon value. Then we compile the model, and here is the summary. And here you can see that we do have here a total parameters of 66 million, and the trainable ones is only 300,000. So this is basically, we're keeping the majority, the knowledge of the pre-trained model, and we're only training those last layers that we added. And those are roughly the 300,000 trainable parameters, but we're freezing the 66 million that is coming from the pre-training. And this is what makes fine-tuning so much faster than training from scratch. All right, I'm generating some callbacks here, and then we can basically fit the model. So we call model fit, pass in the training data set. We want to shuffle number of epics that we define. So we're just going to do one epic in the notebook here, passing the number of steps for training, for validation. And this is pretty fast. This is really just here, you can see 14 seconds, but don't expect too much of an accuracy with a handful of samples here. But we're running this here in the notebook, so just really to understand what's happening. All right, so we evaluate the model with the test data set, and then the resulting model we save here to a temp folder. And you can check the model here, you save it, and then you can check here the folder, and you have your saved model.pb. And you can use the TensorFlow saved model CLI and show the model. And here you can verify the inputs and what the model is expecting here. So with that, we do have our SageMaker, not SageMaker, sorry, the TensorFlow model created. And we can use this here to do a quick prediction to see how the model is performing. And this we can do actually with the help of this Hugging Face transformer libraries as well. So we're pulling in the tokenizer again. We're just setting up a sample review. This product is great. We do the encoding, which generates the tokens and the input IDs here, everything. And then we can call the model.predict. And in this case, the BERT model really just needs the input IDs and the input mask as input parameters. So we're passing in those features and calculating the scores and checking on the prediction. And we can see the results here. So the predicted star rating, not too good. Again, this was just like 10 seconds of training, but it's doing the job. So it generated a star rating classification for the sample. All right, and this was really just for the conceptual understanding of how we're fine-tuning the model. And this was running inside of the notebook just to be really, really quick. And what we're doing next, and I'll just quickly show you here the pipeline, and then we take a break. We're now combining all of those steps, right? So I showed how we do the feature engineering. I showed how we do this fine-tuning step. And we're now taking those concepts and running them at a larger scale. So not in the notebook anymore, but using SageMaker Pipelines. And we're going to execute the feature engineering and the model training using SageMaker Processing Jobs and training jobs. as part of this pipeline. So what I would suggest, because the pipeline will run for 30 minutes, that you start the 07 notebook. So open it and do a run all and make sure that the notebook is starting. So you can see here the numbers are showing up. And just get it started. Don't stop the notebook in between. It will run for 30 minutes. Just keep it running. Do it once. Don't restart it. It will otherwise restart many more pipelines in the background. So we don't want to do this. Open the notebook, start it once, and keep it running. And with that, I'd say we're good for a break, and we'll answer your questions. And after the break, Chris will walk you here through the pipeline, show you how this pipeline is built and what's happening in the background.
Cool. Yeah, so I posted the link to this past Monday's webinar where we had 2 full talks on Feature Store. These are talks that are not part of any conference or anything. We handpicked some people within AWS that know this stuff pretty well. So check that out. Let's see, ignore any errors about libcudart, just ignore that. And make sure, like Ansha said, that you run the pipeline 07, which I actually haven't done, so I need to do it right now. Let 07 run for 30 minutes. Let's take a, what do we say, 15-minute break. Gets us to 12 or to 11. Let's take a 15-minute break. See you in a bit.
All right, we're coming back from the break. Hope you started your pipeline. So let me resume my share here. So make sure you've started, hopefully before the break, everyone, the 07 notebook of the pipelines. And Chris just started a quick pulse check here. So give us quick feedback. How are you doing? And then while you're answering our quick pulse check here, Chris will prepare his pipeline and then walk you through this notebook, what's happening here. All right, looks like most of you are doing good. Few of you are a little bit behind, that's fine. And again, we'll keep up the demo environment for another hour after the workshop. So 1 hour and 43 minutes from now. So you can finish the notebooks after we're done with the workshop, play around, revisit some of the notebooks if you want, and make sure you reading up on everything you wanted to check. All right, Chris, are you ready?
Yeah, I shared my screen. Can you see it? Okay.
Yes.
Okay, yeah, for those of you that maybe are lost, shoot us a private note on what maybe we could have done differently. Thank you for being patient. You know, at scale like this, there's a very large number of people, so which we are used to working with. It's just sometimes difficult to please, 100% of the people. So we try to shoot for, like an 80%. Yeah, anything, we could do to get that closer to 100, let us know. People come from all different backgrounds and all different, and so the best we could do is just try to go down the middle. Okay, so check on 07 here. Oh, I'm in the wrong. Let me close down a bunch of stuff. So if you started the pipeline when at the break, we should be about 20 minutes into it. It takes about 30 minutes to complete. And just to warn you, the results are not going to be super great on this pipeline, but because we are only training for about 30 minutes, usually I think it takes about an hour, maybe like an hour and a half to start getting up to the 70, 80, 90% range. And for the book, we used, let's see, how many GPUs did we use? Like something like 200 GPUs or something crazy. We used the newer 24D the P4 24DNs, which are just monster GPUs for the book, and we were getting like 98.9% or something like that. We don't have time, obviously, to do that today, but we're just giving you the building blocks so that you can do this on your own and apply to your own data sets as well. One thing I want to point out before we start in on the pipeline stuff, in the bottom left here of Studio, you can actually go and look at the feature store if you want. So earlier we created a feature store. You can double click there and you can see, offline, what's the S3 bucket used for that. And we could see the feature definition. So these are all the features that we stored. Feature store does not, feature store does not care what, if you're using PyTorch or TensorFlow, feature store supports everything. Feature store is just, think of it just as a way to store features and add some, metadata, do some time travel. Date is this is a required field for all of the entries. So this is the date that you ingest the data. If you have your own date, then you would use another date field here. But this is the date of the actual feature when it was generated. This way I can time travel back to earlier times, like I said, time travel here. And so this is, if we wanted to actually run a query, we would copy this. This actually doesn't let us run the query, but we did this earlier where we looked at the data in the feature store. Time travel, this is where you would put in a different timestamp. So I want the features as of, Chris Fregley from 2019, and let's train a model on that. There will be quite a lot of innovation this year, more on Feature Store as we get feedback from customers, typical Amazon working backwards from the customer. So if you start using it, you will certainly have influence on how the product forms. The other thing too, you could actually look at your pipeline here. So, this is bottom left here, pipeline. You could double click. Looks like it started 23 minutes, so we've probably got about another 7 minutes. Note that there's two different graphs. This is sort of the description graph. If some of you are seeing just a gray thing, you're actually in the, like more of the graph definition. You want to go into a specific actual like execution. So here we're progressing to the step where we take a look and compare the accuracy and see if it's good enough to push to production. We can see all the parameters that we pass into our, and I'm showing you the end results, and we will then go through the notebook and show how we got here. So yeah, this is, and if you had multiple of these executions running, you would see them running. I think we've built the code such that you can only run one right now. We had quite a lot of people yesterday when we did this internally that ran the notebook like 3 times, and they had 3 different things here. So just run the notebook once. Yeah, Ansha, do we see any comments in the Slack about failed executions or anything?
Not so far.
Okay, big change from yesterday where we had.
Seems everyone is listening and excited to see the outcomes of the pipelines.
Yeah.
I get a thumbs up here. Okay.
Cool.
Yeah,
Okay.
keep going.
And when we deploy the model here in a bit, we'll see model registry and then model endpoints. Endpoints, if you think of it like a REST endpoint, yeah, it's a SageMaker endpoint, also supports gRPC for those of you in the TensorFlow community that typically use gRPC, or yeah, any community that uses gRPC instead of REST. All right, so let me minimize that, give us some space back here. So to give you context, I'm in Quick Start and I'm in 07 Create. This is what we've been running. We have a couple more notebooks after this. This is really creating the pipeline definition and then launching and starting the actual execution. So this is what we're building. This is what I was just showing you. And then throughout the notebook, I show where we are in the actual execution. So this horizontal view is really this same view, but just kind of flattened horizontally. So yeah, like nothing really surprising here. It's just a slightly different way to show the pipeline, just a little bit more space conscious. So here's some of the boilerplate that we saw in most of the previous notebooks where we're setting up the SageMaker session. So this notebook is starting from raw data, and we're actually using the TSVs here. So this, like Amazon Reviews customer reviews data set comes in 2 flavors, comes in Parquet and comes in TSV, which is like tab separated. Earlier, we had imported the Parquet so that we can do the phase 1 of this workshop, which was doing the analysis and sort of analytics and taking a look at what's in our data set. Then we visualized it, then we checked for imbalances and bias, and then we kind of walked you through what we're going to do now as part of this pipeline, which is feature engineering and then fine-tuning BERT. So this pipeline starts with the raw data in TSV. Now, we are using TSV instead of Parquet because we're not actually doing an analytics workload here. Yes, analytics is typically summing up columns, doing averages on columns. We are looking at columns. When we're training models, we're actually looking at rows of data. And so this is where TSVs actually aren't that bad. Now, I think Ansha mentioned earlier where we very quickly take the raw TSV, which is not very space efficient, and trim it down. We split the data, we balance the data, and then convert it into what's called TF record. So Ansha showed you the snippet of that code from 05, I believe, and I'll show you how that code gets worked into this pipeline. But just know that we're starting from TSV. We're actually going to just choose a subset to keep this a little bit lighter and to match what we were analyzing before, which was just a subset, digital software, digital video games, gift card. Our favorite gift card with the highest average rating, which makes sense. And we're going to just create an arbitrary pipeline name. This we'll see actually right here, in the name. It's just using timestamp just to give us something unique. You could call that whatever you want. And now this is pretty important piece of pipeline knowledge. So now this is the brand new SageMaker Pipelines that was released in December of 2020, just a few months ago. And if you've ever done any Airflow or done Kubeflow, you'll know that the first step to creating a pipeline or a workflow is to define the graph of execution. And so this is really a graph. I mean, it's a pretty simple graph to begin with, and then we end up with this condition step that then conditionally will either stop the pipeline if the model does not have good accuracy based on some threshold that we provide, or if it is higher than the threshold that we provide, it's going to then deploy the model. Now, there's actually one extra step to the deployment. This model really goes into, basically a staging state where the model has not yet been pushed. A human comes in, or we can programmatically push to production as well. So I'll show that here in a bit. So this first step is processing. That's really what we did here in the 05. When we did the feature engineering, is this processing step. So Ansha really talked about this, so I'll kind of skim over it, but basically we're converting this review body text into these BERT vectors. The important part here was these parameters. So these parameters are really placeholders. And so when you're building up these graphs of execution, you aren't actually executing anything. You're just defining what you want done. And so SageMaker Pipelines has this concept of what's called parameters. And you could have integers, strings, floats are the three that we're using today. And we're going to then define, so we have the raw input, which is a bucket in S3. So we physically copy this data from the public data set into a private bucket just to simulate, that you can use your own data, right? So we were analyzing previously on the full public data set, but we can actually pull this data in locally. And I would recommend pulling it in locally. It's a one-time thing, just get the data in, and now all of your queries and your training will be much faster because this data lives inside of your account. Okay, so we're going to define some of the parameters that are going to be used to. So what Ansha showed you was in the notebook. We typically call this ad hoc. Now we're going to do it at scale and use a processing job. So we showed processing jobs a little bit earlier, very generic, very powerful. They're basically, any form or free form script, if it's a Python script or a JavaScript or a Spark script, PySpark or Scala Spark, can run in processing jobs. So that's what we will do today. These are the parameters that we're going to pass in to this feature engineering processing job. If you notice, we're also defining feature store. So this pipeline will actually populate a new feature store. We could have used the previous feature store that we created before, but just to kind of decouple these notebooks, we create a new feature store here, or feature group. And here's this processing job. So I think Ansha showed this earlier with like the imbalance stuff, and she passed in a, the necessary like configuration to run bias detection with the processing job. Here, we're using just a generic scikit-learn processing job, which is really just a Python processing job, simple processing, like Docker image. That just so happens to have scikit-learn 023.1 installed. That's pre-installed for us. We can actually provide our own Docker image. Maybe we have our own custom security, or scanning rules on our Docker images. We don't trust the, SageMaker ones for whatever reason, even though we scan our own images and keep them very clean. But if you want to provide your own Docker image, you could certainly do that. I always think of this as just a sort of generic Python processor. Most workloads that we do have some bit of scikit-learn, either looking at metrics or doing some splitting. So yeah, that's exactly what we're going to use scikit-learn for here, is splitting data. And by splitting, I mean splitting into train, validation, and test data sets. So when we train, we're going to train and then validate. When we go to actually look at that model after it's been trained, we then use this third holdout data set called the test data set to give us one more look. And this data is not seen during training. So this data is valuable to have these three. This is why they typically always talk about 3 splits. Yeah. And if you've heard of k-means cross, k-folds cross validation, that's for, so we specifically do not use k-folds cross validation because we have a lot of data. K-folds cross validation is sort of a classical technique when you don't have a lot of data and you want to alternate the role, so the same row of data with k-folds will act as train and then validate and then potentially test, and can flip-flop between those 3 depending on the sort of randomness that those folds are chosen. So we don't need to do any of that. We have tons of data. We're just like physically going to split the data. We are also going to balance the data. So I'll show you that code here in a sec. This is where all that code lives. So this is inputs into this script that I'm about to show you. This is the outputs. So this is the raw TSVs, and then we are going to output TF records that are split and balanced. And all that happens in this pre-process script, which is down here. So let me do a little side-by-side action. So this script on the right, this is actually using SageMaker. It's using transformers, using TensorFlow. So we are using transformers here because we're going to use BERT to create both like the input IDs, the input mask, and all the things that are needed by the next training step. So I'm going to skip over this for time's sake. This is where, and we will also, so this script does 2 things. It puts data into the feature store and it creates the like TF records. And we could potentially store the TF record in the feature store. We've chosen not to because we actually want to have the like TF record file, which I'll explain here why in a bit. But just know that the output of this is going to be TF records in S3. And then also our data is populated, our split data, and the input IDs and all of the things that are in the TF record will be in the feature store as well. Here's the tokenizer. I think Ansha mentioned we're using a slight variant of the base BERT model that is about 96, 97% just as accurate, but much more memory efficient. And So this is the English version, and this is called DistillBERT. It was created using distillation, which is a statistical term you can look up. There's a paper on this actually by the Hugging Face, that same company. So let me skip through here. This is just setting up all the feature store, defining what's in our feature store. We saw this in the notebooks earlier, but this is the sort of at scale version. Yeah, so that's the key. Some of you might be asking, well, why is this different than what we did in the notebook? In the notebook, we operated on very, very simple data, very small data. Now we are now opening this up to much larger data. All right, and all of this, the sort of interesting stuff here is this is where we're actually taking the review and converting it into those input IDs. Okay, so that's the output here. And then the attention mask, also called the input mask, depending on which library you use or what paper you're reading, they'll use those interchangeably. Some stuff commented out here we were using for debugging last night, I believe. And this is where we actually create the TF record. So TensorFlow loves TF record. TF record, think of it like, sort of binary packed version of our data set that we're going to use to train. And, TensorFlow reads it like natively, very, very packed, very efficient. This is not compatible with PyTorch, by the way. TF record is specific to TensorFlow. For our PyTorch workloads, we just end up using CSVs typically. Google who created TensorFlow loves protocol buffers. TF record is based on protocol buffers, which is binary, non-human readable, but very efficient. Yeah, anything that's not human readable is likely machine efficient, is sort of the intuition there. Okay, all this comes together. Here's where we're parsing all of these parameters here on the left. So and then here comes the balancing. So this is where we balance. In some cases, maybe we don't want to balance. Typically here we are balancing. So this is where we're using some of the scikit-learn. So fortunately, that's part of our processing job Docker image. We're then splitting. So we are splitting, and that's some of the parameters passed into this processing job. 90% we're going to use for training, 5% for validation, 5% for split. You can tune this how you want. This seems to work okay for us. So now the output, and then this is just a bunch of boilerplate kind of converting into data frames. This is where we're actually writing out those TF record files. This is the protocol buffer based binary format. Now we're actually populating the feature store. And again, I'll explain a little bit more about why we're doing both the feature store and the files. There's certain cases where we want to use the files and certain cases where we want to use feature store. For our purpose today, we store them in both, and then that gives us more options later. And then the rest of this is just reading in all those files that are being passed. So those three tsv.gz files. Okay, so let me close that out and get back to. So that's this step here. Refresh that. Hang on here. Oh, this one succeeded. That's the one I want. Okay, let me close that. So our pipeline finished, by the way. Looks like it took 29 minutes. So this step, this processing step is this step right here. And this blob, we've asked the studio team to get rid of this blob. It's super annoying, but this processing step is this step right here. And it looks like the output was into these three S3 buckets. We could see maybe if we copy this. Here we could see the logs from that processing job, right? So again, whatever we print inside of this script will show up in our logs here. So it's just scraping Docker logs and doing very familiar things. This is the input. So what kind of instance type were we using? What's the actual data source of the data, which is that bucket where we copied those 3 TSV files. Yeah, Ansha, yes, any questions before I jump to the train?
Yeah, a few people asked around the splitting of the data, so where we put it, and you just showed it here as part of the pre-processing script. Other people asked if we need TF record and if it's possible to use BERT independent of TensorFlow. So yeah, definitely. So TF record is really just an optimization for training with TensorFlow. It's not mandatory. And I also just pointed out that, for example, the Hugging Face Transformer library also offers the models, for example, for PyTorch. And it's really just an implementation choice. So we picked the TensorFlow one, and we just decided to optimize and also create those TF record files, but it's definitely not mandatory. Maybe you want to elaborate a little bit more, Chris.
Yeah, no, that's it exactly. It's just an optimization. We like it because it shows a little bit more complexity to our feature engineering pipeline. Yeah, otherwise the narrative is just that it's splitting data and balancing data, which is very common, but we just wanted a tiny bit more complexity. So yeah. Okay, so let me keep going with train. So after this data is processed, we're going to pipe that data in. So we want to use the output of the previous step to put into as the input to this training step. And so I'll show you how some of that's wired up here. These are hyperparameters that are being passed in to the actual training job. So this is, if you wanted to, get better accuracy, I think we end up with like 30% accuracy, which isn't that great. But if we train for a little bit longer and bigger batch sizes, things like that, we would get some better results like we show in the book. And I'll just kind of skip through some of this, but the key here is that the output, and so here's where we actually specify our training job. So actually, let me talk a little bit more about what's powering this train step. That is in TF BERT reviews. So this is the equivalent, or not the equivalent. This is similar to how I was showing the processing job before. This is the actual Python code that's also using transformers, also using some scikit. We're even actually generating a confusion matrix here so that we could package it up. And whenever we have our model, I could also see quickly the confusion matrix, just a little kind of development time optimization. And so without getting into too much detail, because we only have about 15 minutes left here, this is where we are decoding the output of the previous. So like I said, the output of the previous step is a TF record. You don't have to use TF record, but we are. This is where we're decoding it and then handing it over to TensorFlow. And so TensorFlow actually uses this and prefers this. Also, there's some checkpointing we can do. I'm not going to talk too much about that, but if you are using spot instances, which are supported for SageMaker, and you lose a spot instance during training, we can recover, or if, just sort of any failure happens, we could always go back to the previous checkpoint, which maybe we checkpoint every 5 minutes or hour or something like that. That way we don't lose the entire thing. Like, this doesn't happen often, but if you are using spot instances, this could happen. So you do want to checkpoint when you're using spot instances, which are 90% cheaper. The problem is you are given 10 minutes of warning, and your SageMaker job will halt until it can get another spot instance, and then will ultimately fail if you can't get a spot instance within some threshold that you provide. But the good news is with checkpointing, you can then start up a new training job that uses all of the learnings from that were stored inside of that checkpoint. All right, some pretty boilerplate code here. This is really where we start setting up the model and setting up the data. Here we get the model. This is where we are actually setting up the model and adding that classification layer on top right here. So yeah, so like Ansha mentioned, we are using BERT as the pre-trained model. We are then adding a custom classification layer. This is all actually very, very simple classification neural network stuff on top of the base distill BERT, that like pre-trained model. This is the pre-trained model. This is that fine tuning part here. We're giving it the 5 classes, 1, 2, 3, 4, 5, that represent the values of our star rating, and then training this model. Doing any checkpointing if it's configured. Here's where we're setting up our stochastic gradient descent optimizer. This is a variant called Atom that has its own hyperparameters of epsilon and learning rate. Here's our loss function. There's the metric. So this is all numerical optimization speak here. Pretty straightforward. And then we train our model. We also have some flags here to do some tests and generate some confusion matrices. This is where we're actually saving the model. And this is what we actually end up deploying. Okay, so all of that does some sample predictions and calculates some of the accuracy. Let's go to the next notebook, actually real quick. Well, I haven't quite finished this one yet. Okay, one sec here. Let me finish this. Let me close that. So after training, so this training step is this train right here. Train equals that. Next, we're going to take a look. So the output of train includes whether or not this, or what the actual accuracy was of this model. So, and this next step is another processing job, very, very lightweight, very simple. That's a script that just looks at the output that was generated, or no, sorry, this script actually runs a sample, uses the test data split, and then calculates its own test accuracy. So this is a pretty simple one. I'm going to skip through it for time, but all we're doing is just calculating accuracy, making a bunch of sample predictions, calculating accuracy, writing it to this JSON file, and that's what then gets picked up by this next step, which is the accuracy condition. So some of you might be thinking, this is absolutely crazy. Why am I doing all this? I could train a model with a simple notebook, and you certainly can. And that's sort of like MLOps 1.0, right? Where you're just training models and doing it by hand and writing some scripts, and yeah, that's totally fine. But then there's MLOps 2.0, which is pipelines and being able to start to automate these things and not be maintaining scripts, but be focusing more on the actual modeling and the business rules. So, some of us just have not seen the need, right? Yeah, some of the people on this call maybe have not seen the need for pipelines, but when you start to get in situations where you need to reproduce these models and continue to train as new data comes in, this is where the sort of MLOps 2.0 and then what we describe in the book as MLOps 3.0, which is now I can trigger these pipelines. So with MLOps 1.0, we're just creating models. With MLOps 2.0, we are actually building pipelines that feed those models and train the models. And then with MLOps 3.0, we are triggering models based on either new data coming in, which is the most common. As new data comes in, we want to continuously train, or maybe we made a small change or using different hyperparameter, and now we want to trigger a new model. Okay, so yeah, like I said, all this seems kind of crazy and seems kind of overkill. I hear this all the time. But just know that we would not have built something that customers were not asking for, right? And so there's things like Airflow that have been doing sort of pipelines of like data engineering for a very long time, very, very popular projects. Yeah, the other big release that came out during reInvent December 2020, a couple months ago, was managed Airflow. So you can check out that service. And we actually have an example in the workshop in the pipelines that we don't have time for today. But and yeah, so we have heard this from many customers that they want automated ways so that they don't have to keep thinking about this stuff. They can write this code once. So this processing step, which is the evaluate step here, this thing takes a look at the output of the train, which is the trained model. It then pulls that model in. It runs a bunch of sample predictions. It then calculates the test accuracy, which is different than the train accuracy or the validation accuracy that was calculated during the train step. So it's a third way to measure the accuracy and of your trained model. So and before I could talk about the condition step, we have to tackle these leaves of this tree, of this graph first. So one of the paths is if the accuracy is sufficient, we're then going to register the model in the model registry and then create it and get it ready for deployment. We won't actually deploy it until we run, I think, the next notebook, or yeah, one of the next two notebooks, because of the and that's on purpose. Now, there is a way to just automatically push it out, but we do want some human control for this example. In some cases, you don't necessarily need human control, and that's certainly doable with SageMaker Pipelines as well. All right, so the rest of this is really just telling it to use TensorFlow serving. So this is a SageMaker container that uses the open source TensorFlow serving and packages that up, and then has like many optimizations built in for the AWS infrastructure. Here's where we register the model. Here's where we create the model for deployment. So that's this step here. And now we can build the conditional that depends on those two leaves. So here's where we actually have a parameter for the threshold. Now I set this threshold really low. We could probably bump this up. I think we get about 30%. So, maybe we would say if it's above, 30%, then deploy it. You can also configure this to look at the previous run and have it condition off of the previous model's accuracy. So that's something we see people do. All right, and then if the success, it's going to then register and then create. If it fails, we're just going to end the pipeline. So now all of this comes together. We create this pipeline. This is the actual pipeline definition. We then create it. We then start it. We can override these parameters as we wish. Here I'm just using the same hyperparameters we've been using in the notebook examples. And this is where I could actually override and say automatically approve, or is it going to wait for manual? And this already ran, so I could skip through all this. We see all these steps came out successful. If you did actually have any failures, you would see failures here. You would also see it in this UI as well. And now the really cool thing about SageMaker Pipelines that I want to emphasize is all of this really comes together now. So December 2020 was a huge month and huge set of releases for SageMaker. This is where we saw lineage tracking, we saw artifact tracking, we see the experiment stuff coming together, we see pipelines. So now there's this whole sort of ecosystem that all comes together, and we can actually take a look at what was generated here, both programmatically and through a UI to see all the artifacts. So this is our processing job. So this was the processing job script. That was the input. That all contributed to these outputs, which is the TF records. This is our training step. So here, and so this is lineage. So I can actually query and say, for a deployed model, tell me what like data set was used. If we were using like feature store here, for example, I could see the exact feature store query that was being used. Here we're using the files. We can also see which Docker images were used, what was the actual source, the source code used to process. We can look at the version that was in S3 for the raw data set. So all of this stuff comes together now under one API, which is super awesome. And then when we go to deploy the model, we see that it was set up for manual approval. We will then, in the next steps, actually push these out to production by marking them as approved. All right, so that built up the whole thing, ran the pipeline. Let's go to evaluate the pipeline. I think this is probably, I still haven't run this. This is probably a pretty light notebook, if I recall. Oh, okay, so we actually got 44%. Yeah, so this isn't actually doing much except looking and asking the pipeline, what was your accuracy? So this is pretty light. Oh yeah, this also grabs the model, takes a look at it, makes sure everything looks good. I do this. This is a TensorFlow specific thing, but I like to take a look at this model and make sure the signature matches what I think it is. So here we see the BERT. So these are the two inputs into BERT, which are 64 max sequence length for the input IDs and for the attention mask. And the output is a distribution over 1 through 5. Okay, and then we would do argmax to figure out what's the highest. So these end up being confidences that 1, 2, 3, 4, or 5 is the best prediction. We take the highest, and then that's the actual answer. That's the actual prediction. All right, and more about the lineage. I don't think there's anything more here, actually. So, and then let's see, register. So this is, let's just do a quick run all here since we're almost out of time. And let's get this model deployed. I think this step takes about 5 minutes or so. So yeah, any questions, Ancha, while the deploy stuff is happening?
Yeah, so there's a question for the model deployment, if the SageMaker ecosystem supports model ensembles in some way.
Yeah, we've heard this question. There is an answer to this. Either, yeah, I actually can't remember the answer. I've seen Ali talking about this a few times. We could probably ping him on Monday. There's ways to package up multiple models within a single endpoint. I just don't remember how to ensemble the predictions. So the short answer is you can do anything inside of your model endpoint. And in fact, I'll show you our model endpoint is actually quite a simple. So this is inference.py is typically what it's called. And this is handling, taking any type of input. For us, this is, JSON coming in, and then we're constructing JSON and then responding with that prediction. So I've seen people actually where they implement their own custom inference handler here for the input and then making multiple calls here. I've seen that way, but yeah, model ensemble, we have a story for it. I just can't remember. Yeah, like we'd have to Google for that. All right, let me check. So we should be able to inspect. So I should be able to go bottom left and look at the model registry. Okay, here's our model registry, which we see there's our model that we had created and then registered during our pipeline. And I didn't show it earlier, but this previously said it was pending for the approval. Now we see that that it has been approved, and we're, oh, I saw somebody ask in Slack about monitoring bias after the model has been trained, which we actually talk about in the book. Even though you balance or get rid of bias in your data set, that doesn't always completely get rid of bias in your model. There's still times when your model could learn some patterns that you weren't expecting, and you can balance all you want, but for some reason the model has focused in on one part of the image, or one piece of your text corpus. So you want to do what's called pre-training bias, which is what Ansha showed earlier, and post-training bias, which we don't have time for today, but we do cover in the book, and there's examples in the code in the full 15-hour workshop. But yeah, you want to be cautious. Now, you will help that situation by balancing beforehand. But there are also model quality metrics, which we don't have set up here today, where you can establish a baseline, and you can give that to your model endpoint and say, here's a baseline set of reviews, and here's the, and that baseline, so that typically comes from your training data. And so you can tell your endpoint through SageMaker to say, this is a baseline, calculate the statistics on this baseline. And if in real time, my model starts to make weird, it starts to like diverge from that distribution of the baseline, then something is wrong and possibly retrain. And so you could set up alerts and get paged at 3 in the morning as a data scientist, get paged that your model is now making predictions that you were not expecting it to make based on some distribution of your training data. So that's one form of sort of real-time model quality analysis, and drift is commonly the term there. There's also a case where we can detect those and pass them to humans, and have humans actually relabel these things. So, and while the human is not part of the request response, that human will see these, potentially poor predictions and can correct them and put that data back into a pipeline. And so this requires ground truth, and specifically there's a service SageMaker has that's called ground truth, and yeah, not by coincidence. So but these humans can then label this data, and you can set thresholds and say, I want this data to be looked at within the next 3 days. If it's not addressed within 3 days, then throw it out. It does not mean that the application is waiting 3 days to get that prediction. That prediction still comes back in real time. It's just we are giving humans a chance to review these predictions and either correct them or acknowledge them. And then that data gets put back into the training pool, back into your feature store or back into a TF record. And then the model on the next training and push will be improved. Okay, let's go back to the endpoint here. Looks like it's still deploying. We can actually take a look at the endpoint. If you click on this deep link here, it'll take us. Looks like it's still creating. There's really not much more that's interesting here. We could see the invocation metrics. Let's just give it a little bit of time to settle down. This is the data capture feature I had mentioned earlier, where we could capture the inputs and the outputs in real time, sample them. Here's the sampling percentage. And if we then find, and constantly compare it to some baseline. This is a little bit complex to set up, which is why we don't do it here today. But once this is running, like this is very effective at catching drift. And, catching drift in both the inputs that are coming in for these predictions and catching divergence of the distribution of the actual outputs. So the 1, 2, 3, 4, and 5, if suddenly we start seeing a huge spike in 2s, and our training data set, which we analyzed earlier today, had a very, very small amount of 2s relative to 5s, but now all of a sudden we're seeing a whole bunch of 2s and not 5s, something is probably wrong. And so that's the kind of real-time model monitoring we can do. Yeah, anything else, Sancha?
Yeah, so I'll just look up the link for Model Monitor. So question, we haven't implemented this finally yet. We've been starting doing it. But basically where you would do this is to set up what we call a model monitor, which will, what Chris just showed, which will monitor the predictions coming in. And to detect the baseline drift, you would need to provide the baseline and then also have a job going on that is capturing the predictions. And it's basically getting ground truth data. So you would have to annotate those predictions, provide the labels, and upload them again. So the job that then runs can detect the drift. So it's a little bit more step process to set this up, but it's part of, if you look for Clarify and Model Monitor, and I'll get you the link here. Question, do we have samples about best practices about quantization or things to improve inference? I think that's a topic for you, Chris.
Yeah, let's see, let me get back. So yeah, we've got some, I think it's in the work or the, O9 deploy. I think we have some inference because, or some quantization, we are using TensorFlow, and we had a version somewhere where I was using TensorFlow Lite. And also there's a service and a library, open source library called SageMaker Neo that can take your trained model and convert it. Yeah, so maybe, Ancha, we could find the Neo docs, including the open source docs as well. I always keep an eye on the open source. And that'll take your trained model, which could be 700 meg, 800 meg, because these are large models in a lot of modern cases, and can quantize it down into a smaller form that can fit on a cell phone or fit on a sensor. So yeah, there's definitely, that falls under the SageMaker Neo. And there was a new service that was released called Edge Manager, SageMaker Edge, that can actually monitor those and swap out new models and help deploy the models. That sort of overlaps with the IoT part of the AWS stack. All right, so let's take a look. And at some point, this is going to deploy, and then we're going to run a bunch of predictions. This is great, this is bad, and that's the end of the workshop. So this deploys something called pipeline endpoint name. And you don't have to do this because we're going to tear these down at about 1 o'clock today Pacific time and in 1 hour. So don't worry about cleaning up. But if you are running this on your own, you would want to clean up this endpoint when you're done. Yeah, any other questions, Ancha?
Just a couple of follow-up questions here. People are excited about the detecting the drift from deployed models. Yeah. Whether we can use the model monitor with models deployed at the edge.
Yeah, I think because it's part of SageMaker. I thought I saw that while we were writing the book. I remember thinking about that.
So probably using the Edge Manager in that case, right?
Right. And I remember thinking, oh yeah, that's right. I didn't think about that. It's either there or coming or something. Yeah. It was one of the benefits of using Edge Manager was that we can reuse these kind of features from SageMaker. Yep.
We'll get you more info on that.
And for those of you that wanted to do the Kubeflow stuff, if you want to start it now, if you're not completely worn out, you could try to run through, set up EKS. This will take you the next hour for sure. It's a little bit of a tricky transition here, and it's mostly sitting around waiting for EKS to start up. The Kubeflow is pretty quick, and then we actually build up it's the same exact BERT model that we just built with SageMaker pipelines, but we use Kubeflow pipelines to coordinate. And so some of you might ask, well, why would I use Kubeflow? Or, on the contrary, why would I use SageMaker pipelines when I'm using Kubeflow pipelines? Or, why would I use SageMaker if I'm already using Airflow? And so, by the way, yeah, we do have Airflow example here that was contributed actually by one of our peers just in the last week or so. So this is using the new managed Airflow service that is, which is huge, by the way. We've seen so many customers that have been switching over. They just don't want to manage their own Airflow, or they were tired of upgrading, or whatever. Cost of humans, while it's not like super extreme, it's still pretty like significant, and there's still other things that humans should be working on instead of upgrading your Airflow cluster. This is something I didn't necessarily buy into until I had my own startup before joining AWS, and I was just so worn out from trying to manage Grafana and Prometheus, and it's fun and I love it as an engineer and as a problem solver. I just have come to realize that I have other problems that I want to solve, and I was kind of tired of solving the same logging and getting the ELK stack or the Fluentd the EFK stack running. I just didn't want to do that anymore. And when you start getting into more like data science tasks, and you're on that edge of like ML and ops, my personal preference is I have now moved more towards the ML side. There's so many very interesting sort of business problems, and after 20 years of this, I was just kind of tired of redoing all this. So yeah, I realize I'm talking to people that have either made their decision, they already use Airflow, they might already use Kubeflow and have a huge commitment to Kubernetes, and I certainly can't change your mind. You would not have been able to change my mind 3 or 4 years ago, and after 3 years of that constant upgrading and always being on call, not for data science reasons, but being on call because of a bad configuration that I pushed, or co-founder pushed, or something like that. So it's your decision, where you want to focus. But yeah, it's pretty straightforward. You could follow these notebooks, get through this. Will pull down kubectl. I think it's kubeflow 1.1 or 1.2 or something. But yeah, SageMaker pipelines, the benefit. So if you're using Kubernetes today, and you want to use SageMaker for the heavy lifting on the ML side, then use this integration. So there is first-class integration between Kubeflow and SageMaker, and we show completely open source version where you're not using SageMaker, and we show a kind of best of both worlds, both Kubeflow and SageMaker version here as well too, where we actually build up the same exact pipeline, but with Kubeflow, and then same with Airflow up above as well. All right, let me check on the model here. Uh-oh. Yeah, Ansha, did your model deploy?
My model deployed. Yeah.
I wonder what happened here.
I can show mine.
Yeah, can you grab the screen and make some predictions?
Yeah, let me just quickly get my screen share from you. And select the screen here. All right, so yeah, my model deployed. So just quickly showing you, let me zoom in again. Make this a little bit smaller here. All right, so deploy the model, the last notebook we had here, setting up, showing the pipeline execution steps here again, viewing the registered model. So we're checking out basically the model from the model registry. So we're getting here the package ARN. So that's the identifier where to find the model. Here is the model name. And the last one here, basically the pipelines one. And what we need to do, we create a model endpoint. So this is the hosting endpoint. We create the model and create the endpoint configuration. So here we specify which type of instance. So we're going to deploy on an ML-M5 4x large instance with initially one instance, and this can scale up when the traffic gets more towards the model. And then basically here's a deep link. So we're creating this endpoint here, passing in the endpoint name and the configuration. And then here's the deep link that takes you to the console. And you can also see this here if you go to inference endpoints. There should be the one model. It's taking roughly 5-6 minutes for the endpoint to be created because it spins up the EC2 instance and then loads the model and the image, the inference image here onto this endpoint. And if you click here, you can see here is the REST API where you can call and get the predictions. So you can embed this into your applications. And we can also query it from the notebook. So we do this here at the end. So we're pulling in a TensorFlow predictor, which is part of the SageMaker library here, and giving it the pipeline name, the current session, specifying the name of the model, which is the saved model version 0. We're passing in JSON lines. That's the format that the model expects. And we're specializing here the serializer, deserializer. And this one is really just making sure to parse the JSON lines correctly for the inputs and the outputs. And then we're doing 2 sample requests here. So we're doing an input features. And this is really the model signature that we created. So the model expects the inputs in that format. So one sample, this is great. And we pass in another sample, this is bad. And then we can call the predict on this predictor and give it the inputs and looping through and see the results. And we can see here that we got a predicted label of 5, and for the other one, a predicted label of 1. So the model is predicting, and this is really the example here to show you how to deploy this model as a REST API or behind a REST API, all managed by SageMaker. And we do have one more notebook here, which shows you if you wonder how to clean up that endpoint, maybe if you're deploying this workshop code in your AWS accounts later. Here's the code to then also stop this and delete this model endpoint. I'll keep it running so I can keep predicting here. But yeah, that's the model deployment.
Cool.
All right, Chris, and I think we do have a post-workshop survey before everyone wraps up here.
Yeah. And please give us honest feedback and let us know what you think. Okay, just sifting through quickly. Any other? Oh, is there a way to export the execute? Yeah, best way is to just download the notebooks. You can also tar up the notebooks through a terminal. Here, let me grab my screen. Yeah, Anja, like we have to keep remembering. Someone asked about your font again. It's deceiving with these new monitors. I know.
What's the font?
What is Zoom? Yeah, zooming in.
The Zoom. Yeah.
Different kind of zoom, but yeah, zooming in. So the way I've seen people do this before is you would, for example, CD workshop, I could tar CVZF 00 quick start, boom, 00 quick start. Something like that, boom. You could tar it up, just kind of clever tarring. That'll show up here as a single file. And then I could right click and I can download that single file. Yeah, so thanks for the feedback. Let's see. GitHub repo is here. And book link, I think I've sent 100,000 times. Book link is here. We're very proud of the book. It's been reviewed by many, many people. I'd say probably close to 100 people now, both within Amazon and outside of Amazon. And we've gotten, we spent the first probably 8 months writing it, and then the last, 6 months just incorporating feedback and updating for reInvent, for the most recent reInvent, the most recent launches. So yeah, pretty proud of it. Take a look at that. Ansha, I have already emailed the O'Reilly folks about why it's not showing up in India. And yeah, I know it was not showing up in Germany for some reason, which is where you're based. So
yeah, it's so the local marketplaces, so the German marketplace of Amazon, the US one, the India one, they have their own processes when they list the book. What I figured when I see the German marketplace has it for pre-order, it shows it not available if I have a mismatch, if I'm logged in or not logged in. So make sure you're logged into your Amazon account in your region, and you have the shipping address set to the right region. So if I, for some reason, log in for the US store and have my German shipping address, it also shows up not on stock.
yeah, that's right.
So make sure that's in sync, your shipping address and location. And yeah, if you still find it not available, shoot us a message. We'll figure it out. It's just the local stores, marketplaces have their individual timelines when they list the book.
Excellent. All right. Check for any last minutes. Yeah. Thanks so much, everyone. And if you want to, we will archive this channel. And if you want to move discussion over to the general channel, we've seen, people answering each other's questions over there. I think we've got, see how many people do we have there? 1,500, something like that. Folks over in the general channel. Yeah, so the pipeline has Airflow, Kubeflow. It even has step functions. We see customers that have an investment in the Amazon step functions or as AWS step functions. We have a version that builds the exact same BERT model in step functions as well. There's even TFX. You could see TFX is a very interesting framework. It's kind of a pipeline, but not really. And it has some dependencies on some other technologies like Apache Beam and stuff that I haven't really spent too much time with. But we do talk about it a little bit in the book, and there is an example there. We'll keep the servers up for another 30 minutes, and I think that's it, right, Ansha?
That is it. Thanks everyone for joining us today, and enjoy the rest of your weekend.